like a minute. Just make sure, this is the Intro to C tutoring session, just to make sure everybody's in the right place. My name is Jennifer Brown. I'm going to be leading the session for you guys today. It's offered by SARC. So we're just going to get started here. Oh, sorry. So the review packet, if you guys need to know where that is, let me pull it up real quick. I have posted it to the UCF SARC WordPress.com, COP3223, and it'll see COP final review if you guys don't have that. And that's the packet that we're going to be doing today. So if you need the website, it's there, and it's just that first link at the top. I'll just give you guys a couple minutes to pull that up if you need to. So we're just going to get started here with the intro. So the first thing we're going to do is just variables. So how can we store data in a program? So programs need to allocate memory, right, for things to exist. So we need to have a data type and then a variable name. And that's where our data is going to go. What data type we use is going to determine what type of data goes into that variable. Now in C, you can have valid names for your variables and you can have invalid names for your variables. There is kind of like a set number of rules. So we'll just kind of go over these examples that I've given. So our first example is 9 length. So a variable name cannot start with a number, right? So our 9 length here is not valid. Our compiler's going to yell at us. It's not going to like, what is this 9 doing here? It's looking for like an alphabetical letter or something. Similarly, we have our underscore hello. Variable names can also not start with special characters. So you can't use a hashtag, you can't use an underscore. Those are not going to be valid either. I am super cool name. So this is a valid variable name. It starts with a letter. It's not a keyword. There's nothing, bad about it. So this is valid. All right. So now we have a variable called int. So in the language, it would look like you're trying to do int or like float int. So this is not valid, even though it starts with a letter. This is not valid because it uses a keyword. So in C, there's a set number of keywords that you have. You can have like if, while, for. Those are all keywords. So data types are also keywords, so like float, int, etc. So you can't use them as variable names. So he's going to be like, what is going on? I'm initializing 2 integers at once, and then it's going to get confused and then yell at you. So this is also not valid. Then we have a_new_int. Even though there's a keyword in the variable name, that's okay. Because there's other parts to it. You have like, it starts with a letter, and then it has other like characters in it. So you can use keywords as long as they're accompanied by like other things or a number or something. That's okay. C will not yell at you if there's a keyword in it as long as there's something else to it. So this is valid. And then we just have string 1. You can use numbers and characters in your variable names as long as it starts with a letter first. So this is valid. All right. Any questions, comments, concerns about valid variable names that you can use? All right. This is kind of basics, but a lot of times you are tested. Like they'll give you like, is this valid to use this variable name? going to talk about assignment. So in your programs, you're going to be creating like variables, and you use like int a, etc. And a lot of times you need to assign values to those variables that you created, because like otherwise, what's the point? You created them so that like a number or a character or something can go into them. So when you're assigning, you have to make sure you're going the right way. So in this first example, we have a 3 equals n. So C does not like having the L value on the left there. So if you have the number equals the thing, it's going to try to put n into variable name 3, and 3 is not a valid variable name. Yes? Can I what? Zoom in? Yes, absolutely. Is that easier to see? Is that good? Sweet. So it's going to try to put n into 3. 3 is not a valid variable name. It also doesn't exist, and you also can't like initialize it. So this is bad. This is not valid. Our second example is exactly how you want to do it. So if we have an int n at the beginning, and then we assign 5 to n, we're a-okay. Now in memory, we have a variable called n, and then 5 goes into it. This means that it reads from right to left when you have assignment. So now we have arithmetic. So C follows the same kind of arithmetic rules that you've learned since like elementary and middle school, right? It uses PEMDAS, which is parentheses, exponent, multiplication, division, addition, and subtraction. You don't really have the exponent except if you have like a math function, but the rest of it kind of holds true. So the first thing C is going to look for is like a parentheses. That's the first thing it's going to look out for. And then afterwards it'll look for multiplication and addition and subtraction. There are also other precedent rules for things like prefix and postfix, and we'll get into that a little bit later. So our first example here is n equals 3 plus 4 divided by 2 times 7. So the first thing it's going to execute is this 4 divided by 2. 4 divided by 2 is 2, and then 2 times 7 is 14, and then it will add the 3 at the end, so you get 17. Our second example here, it's going to see the parentheses first, so we'll add these first. So it'll do 3 plus 4, and then you get 7. Then it'll do 7 divided by 2. Now there's something happening here with the 7 divided by 2. Our integer, our variable is an integer. It doesn't take in decimals. So the second it sees this decimal, you're going to get 3.5. Integers are going to do something known as truncating. It's going to take this part at the end and say, noperino, you're gone. Integer values don't store decimals. They're not floats. So anytime you have something like this at the end, it's just going to lop it off. It's going to be gone. So now instead we have 3 times 7, which is 21. So it'll give us 21. Because it's not going to take that 3.5 and use it for anything. It's like, that 0.5, it doesn't exist to me, right? Because this is an integer. However, if you have a float or something like that, it's okay with that. It will use the 0.5, just not if it's like an integer, etc. Our example number 3, same thing. It's going to read these parentheses first. So you're going to get like a negative 7 times 4, give you negative 28. Common mistake here is these two examples. In math class, these are valid. This means multiplication. However, in your C compiler, it doesn't know that, and so it's going to see this and be like, what is going on? So this isn't valid. Neither of these are valid, right? Because it doesn't know that in between here is multiplication. It needs it. So what you would have to do in order to make this one valid is you have to do 4 times 1 plus 2 like that. Thank you. And then over here you would have to put 3 minus 2 times 4 plus 5. like that. So that's what the way you can make those valid. But if you do see those on a test or something, be like, C doesn't read that way. These are not going to be good. So now we're just going to get into precedents. In C, certain operations execute before others. C puts a weight on certain things over others. So in these two operations, the one that's going to actually execute first, and this can be a little confusing, is it's going to be the postfix that executes first. And then it will execute the prefix afterwards. Of course, the difference between postfix and prefix is that postfix will add to that number after it's all done, and then prefix will add to it first. And we can write some printf statements to prove that. So I will pull that up. And this is just to kind of demonstrate what prefix and postfix does. Okay. Can everybody see that? As we can see here, it printed the 0. So it added to, if we write another print statement that has this print I, we can see that indeed it did update. It did change it to 1, but it didn't do it until after our print statement. We will now change it to prefix. And as you can see, it updated first. So that had kind of like a higher precedence. So you just have to keep that in mind. I know in Jahani's class you have like a big chart that you have to kind of have with you. And that will help you out a lot with precedence. Similarly, if you have something like this, actually, I'll do it this way. I'm just going to put a new line character so we can see. What we can see is happening here is it goes to the postfix first. It takes the 0, and then it goes to the prefix, then adds 1 to that. Then when you call I again, then it updates that postfix, so you end up with 0 plus 2 plus 1. So when you have that I in there, it does. And when you call that I, it's just like, okay, I'm going to call the I now, and that's when the postfix is added to it, is when I is called. But it will execute this one first. Then it'll go here. It'll update it to 1. Then it sees the I, and it's just like, okay, now I will add my postfix, and that becomes 2. And as you can see from the second one on the bottom, I is indeed still is 2. Right? No, not what I wanted. Beautiful. Okay, so now we have the tertiary operator. By the way, these first two that we see here are unary operators. And unary means you only need one variable for it to work. So you see I++, you only need I. That's what makes it unary. In plus plus I, you only need I. In tertiary operators, you need 3 things. So what this does is our first example, we have int a equals 3 and b equals 1. This up here will ask a question. It'll say, is a bigger than b? So it'll ask, is a bigger than b? So a is 3 and b is 1. That is indeed true. So that's our question. The first thing that we see here is going to be what executes if it's true. Then the second one is what executes if it's false. So in this case, it's going to return a, because this is true. So this is going to return a. Okay. Similarly, we have is a bigger than b? If so, return a. If not, return b. So in this case, we have 3 and we have 5. So 3 is not bigger than 5, so we will return b. Are there any other tertiary operators? No, this is your only one. This operator works just like an if statement. So it's a very simple if statement. So if you have like one little if statement that has 1 true and 1 false, you can use this operator for it. You probably don't want to use it for anything like more complicated than a single true and false, but there's only one. There's only the one. And the only one that it is a question mark. Question mark for the condition we're asking for, semicolon to divide true and false. Also a little more precedents. We have assignment. What we'll execute first is everything over here on the other side, on the right side of the assignment. So this plus sign is going to execute before this equal sign. So it's not going to just put 3 in there and then add 4 afterwards. It's not what's happening. What's happening in the compiler is it adds 3 and 4 first, and then it assigns it into B. So plus has precedence. Beautiful. Additionally, the plus and equal sign, are they unary or are they binary? So you have to ask, how many variables do I need to make this work? So in our plus example, we needed 3 and we needed 4. We needed 2 things on each side. So that makes it a binary operator in that it needs 2. Similarly, our equal sign will always need like n equals 5, etc. So that's also binary because it needs 2 things in order to work. You can't just put n equals and just leave it like that. Your compiler will indeed yell at you for that. So we're going to get fancy. We're going to go work with the mod operator. So what mod does is it finds the remainder of something. As an example, if we have 3 mod 2, we get 1. And if we have like 1 mod 2, we also get 1. So if it can't divide, it just returns whatever's there. So if you have 3 mod 7, it's just going to return 3, because 3 is less than 7. If you have something bigger than it, then you have to like actually divide into it, and then you have to find out what's left over. If it can go into it another time, then you know that you need to add 1 more to it. So if you have like 4 mod 2, 2 will go into it once. You're left over with 2, so 2 can go into that again, and then you're left with 0. So we can use mod very effectively to determine even or odd, just using mod 2. Mod 2 will always return 0 or 1. 0 if it's even, 1 if it's odd, always. And how can we use mod to restrict range? So kind of the rule for mod is it takes whatever you're modding by, and it goes 0 to 1 minus that thing. That's your range. So if I say I have like %7, mod 7, whatever value I'm going to get has to be in the ranges of 0 and 6. You can almost see mod as a little wheel. And so say, example, we have mod 4. So we have 0, 1, 2, 3. And then it repeats. Oh, let me move that up. And then it repeats. So you can kind of see it as like a wheel. And so that's how you can like restrict ranges. Say if you need something to always be in between two numbers, but it's exponential, it just keeps increasing, but you still want to keep it between like a range, you can use mod to accomplish that, because it's always going to restrict. This becomes very useful when we use the rand operator. So rand is going to return any valid integer. It could be -1,000,000, it could be +1,000,000, it could be 2. You just kind of get whatever it spits out. But a lot of times that's not useful, so we need to use mod to restrict what those numbers are. So if we want 0 to 100, we're not going to want -1,000,000,000, right? That's not helpful for us. So rand, if you recall, you always need an srand, and then you need time, and then you need null. The reason you need this is to seed it. So rand by itself will return the same number over and over and over again. That's not useful. That's not what we want. Right? So rand will give you a random number. It just gives you the same random number. So you need to seed it with srand time null so that we get different numbers every time. And the srand time pulls like from a random time from like 1995 or 1996, and it goes by seconds. So it'll just go a random second off in the distant past, and use that to generate random numbers. So we'll use, and then in order to restrict, use rand. So say if we want 0 to 100. You do a rand 100, that'll give you 0 to 99, right? But that's not useful. We wanted 0 to 100, right? So we have to add 1 and then subtract, right? So then, wait, no, we add 1. And there's like a little formula for that. It's max minus min plus 1 divided by your min for rand. All right. So data types, hooray. So a data type is just telling the variable what it's going to be. The variable needs to know what type of data is going to go into it. And also data types tell you how many bytes and bits you're going to have. So if you have an integer, you're going to have 4 bytes, 32 bits. Float's going to have 8 bytes. Character's going to have 1 byte, etc. So part of what data type is telling it is telling it how many bytes it's going to allocate and then what type of data is going to go in there. So an int creates an integer. A float creates a float. Double creates a double float, which is a float that's twice as long. They just shortened it to double, but it's a double float. Int star is, we will get into pointers a little bit later, but an int star is a pointer to an integer. So it points specifically to an integer value. It contains an address. Void, you will only really see in parameters and functions, and it basically means nothing. You won't initialize nothing in your programs because that's not useful, but when you create functions, then you'll use it a lot more, especially in parameters. All right. Any questions so far? All good? Sweet. Hey, conversion. Yes. What's up?
For the strand time
Yeah, so if you want to do 0 through 100, you have to use the mod operator. Time, all it does is, yeah, it grabs a random second from time and use like a second and a minute from time, and then it uses that to change what number gets outputted. You also have to use the time library, so make sure to include that in your code. Conversion specifiers. These have other names, so if you've heard format code, format specifier, conversion code, they are all the same thing. Certain professors refer it to a certain way, others refer it to a different way. It's all the same. So as long as it's kind of like in the theme of it, usually you see conversion or format and then code or a specifier. It'll be a combination of those. Okay. So when you use printf, what do the following codes display? %D you've probably seen a lot of. It stands for decimal. Decimal meaning your integer values, so it's referring to decimal integers. So if you use %D, you're not going to see like a 0.0, it's going to give you 0, right? Even though you might have a float in your print statement. You might give it a float, but you're like, make it look like an integer. So even though the data type might be different, this will convert it to look like whatever you want it to look like, right? It won't change it inside your variable, but it will make it look different. So you can make a integer look like a float. You can make a float look like an integer by using conversion specifiers. So F is for float. C is for character. LF is for double or long float. And P is for pointer. And this will give you an address. So if you're working with pointers and you need to debug or something, and you want to make sure that your pointer has the correct address, you can use %P to kind of debug. Is it pointing to the right address? Right? You can actually compare it. So if you have like an int A and you have an int star P, you can check it by checking if the A is the same as P. Right? So you can use %P for your ampersand A and %P for your P. They should be the same. So you can use that to debug to make sure your pointers are doing what you want them to do. So it can be useful for debugging in particular. All right. Now we're going to get into the super, super fun thing of functions. So functions are kind of like the lifeblood of programming. They're really, really helpful for allocating certain things, certain methods to like one little block, and then you get to call it. So you have predefined functions in your libraries that you use all the time. For example, printf is a function, scanf is a function. Those are in the standard IO library that you use probably for most of your programming. You've used a printf at some point. Those are functions. Those are predefined. But we don't have to just use predefined functions. We can make our own if we want to. So to just kind of get the feel for functions, we're just going to break down main, because main itself is a function. So main, what data type does main return? So you have this int here, and you have this return here. The data type you see at the beginning is the type of data that it's going to return. So in this case, your main always returns an integer value. And it's always going to return 0 as long as it's completely executed. If you get like exit status -1 or a segfault or something, it means it never reached that 0 at the end. And so it's just like, where's my 0? It didn't happen. So that's really important for your main. But in other functions, you can return other values as long as they're integers. Right? It's not going to return a float. It's not going to return a character. It's going to return an integer, because that's what you said it would do. This next thing here is just your function name. So you can name the functions have the same naming conventions as your variables. They can't start with a number, or special character, or anything like that. They have to be, you know, a letter, and then you can have numbers and characters after that, but they have to follow the same naming conventions. In this case, it's just called main. And then under here, we have something called void. So as we recall before, void means nothing. So what this is saying is, I have a main function. It's called main. It's not going to take anything in. And the reason we put void there is to make sure that if somebody reads our code or we look back at our own code, we know that that function's not taking anything in. If we just leave it as this, it's up in the Netherlands. It could be an unfinished function, who knows, but if we put void, it's like on a legal document where you said, this page is intentionally left blank. That's what void is doing. It's like, I meant to put void. I meant to put nothing. And that's why we use it in parameters. So main will always turn 0. Turns an integer. It takes in no parameters because of the void. Can we have no main function? No, we need one. It can be in another like file. That's linked to it. It could be at the bottom. It could be wherever. But it needs to exist somewhere in order for that program to execute. Similarly, we can only have one. Can't have two. So if you see two mains, it's not going to work. It's going to yell at you. So the clever little void that we keep seeing is, say you have a function that's like void. Function. Maybe it takes it in an integer. This is known as function prototype. So we know it's not going to return a value. It does something. Maybe with that integer, maybe it just prints something to the screen, whatever we have decided that it's going to do. But it won't bring anything back to main. So when main calls it, it's not going to return anything. So in functions, you're going to have something known as pass by value and pass by reference. So when I call, say, a function in main, in this case, in this example, it's going to pass a value, right? Because it's just calling for an integer. It will pass the value of that integer. So if we have like a max function or something, we send two variables with two different values. It takes in those values, puts it into its own variables in its function, and then does what you need it to do. So all we've passed is the numerical value of those things. So that's pass by value. Pass by reference is a little more tricky, because instead of passing just the value, we're passing the address of that value. So instead of saying what it is, we're saying where it is. This is where it's located in memory, so we can access it where it is. And this will look like, as an example, and we will write this function later. So in this case, I just put int star x, but we will write an actual swap function. But this int star means you're passing the address of that thing instead of its actual value. Functions will do one or the other. I mean, not one or the other. You can do both at once. You can send a value and you can send an address, but it doesn't really have any options other than that. You either can send a value or you can send an address. You can't really send much else other than those two things. Okay. Any questions so far about pass by value functions, anything like that? Cool. So writing functions and function prototypes. So this is getting just a little bit more into how we build our own functions and what we need. So as we looked at in main, we need our data type, what data type is going to return. We need what it's called. It needs a name. The name is what you're going to call it in the main function. So in main, if you have a max function, you'll call the name max. Parameters is what it needs to take in. So as an example, like for a max or a min function, it needs to take in two things because it's going to compare two things. You do that pass by value, pass by reference. And then, of course, it needs to return. Void isn't necessary to put return, but you can just put return semicolon. So if you have a void function, it takes an A and maybe just prints something, you can write return like that, just by itself. If you write anything return comma and put anything at the end, if it's a void function, your compiler is going to be like, what is happening here? This is a void function. It's not supposed to return anything. But you can use return. It's also useful if you have like an if statement and you want the function to stop doing what it's doing. You would just write return, and that will end the function. It'll be done after that. You can also do that in main. If you want main to stop, you can put return 0, and it will end. Okay. Okay, so we have two function prototypes here. So this one it's not going to return anything. Its name is swap. It's going to take in two references, the address of A and the address of B. We will write that one up later when we get a little bit more into pointers. In the meantime, we will do an max int function. So it's going to take in an x and it's going to take in a y, and then it will return max. So we have two options here when writing a function. We can either write a prototype at the top and write the function underneath, or I can write the whole function on top. Either way, main is going to need to know what max is before it can call it. So in this case, we can see there's a warning there because it's saying, I don't know what max is yet. So we can do it two ways. We can write the prototype here. As you can see, our warning went away. It now knows what max is. When writing prototypes, you do not need to write a variable name. This is valid, just int. It knows that there's going to be two integers there. It doesn't really need the names because in function prototypes, those only exist for like half a second, if that, like a nanosecond. They just exist to, okay, what am I taking in? I'm going to allocate space for this function, and then they're gone. That's what function prototype scope is. So they'll disappear. We'll make sure to put return 0. And now we can write our max function. In this case, now under here, when we're actually defining the function, now they do need variable names. So we have an int A and an int B. Now remembering what's happening is we're creating two new things. All right, I'm going to go back to the doc. I just want you to understand kind of like the scope of it. We have main, right? This is main. We have an A, and we have a B. A is 5, and B is 7. And they only exist inside of main. So when we call max, we're sending those over to the max function that has its own A and B. And those A and B are allocated when we had our prototypes. So that's why we put int A and int B, because it's creating those in memory now. And they exist only inside the max function. So now 5 went into 5, and 7 went into 7. So there's 4 different variables. They all have the same name, but there's 4 different variables. They just exist in different places in space. And that's a very simple max function. So it checks if A is greater than B, return A, right? A is the greater one. That's what we want to return. And then after that's done, it'll just return B. That's if that thing didn't execute. That's all you need. Because there's returns, so you don't really need, you can write an else in there, it's just not really necessary. Also, if you want to make this a little bit smaller, so is A greater than B, question mark? If so, return A. If not, return B. And that's like just a math function by itself. You can use the Unary operator for that. So in this case, it will return B, right? Because A is not greater than B, so it'll return the B at the end. So like I said, if you have just a very simple if statement, you can use that operator. So it's a really simple way to write a max function. And that way you don't have to bog down your code with all of that. And in this case, we probably want to write, say, like a max that stores it. Why did that go down there? Oh. What happened? It's right there. Oh no, what happened? It's not a function, but it's right here. Interesting. Oh, let's see. Oh, interesting. It doesn't like them together, I guess. Int max. Oh, I named them the same thing. That's what happened. I'm so sorry. I named them the same thing, and then it didn't like it. OK, so as you can see, it returned 7. So we learned a little something today that I actually didn't know. You can't name variable names the same names as your functions. So that's actually really cool. I did not know that. So we know that now. All right. Sorry about that. All right. So we've written that max function. Nope, not what I wanted. So I've written that max function. And that wasn't too bad, but it's just to kind of like boil down, like once you get the simple functions, then more complicated functions become a lot easier because it's like, I know what return types are, and I know what this does. Okay. So we did finish up that, and it did return the biggest number, which was 7. So it did what we wanted it to. Any questions about any of that? Good? Sweet. Decisions. All right, so decisions are our conditional statements. The keyword that we use is if. In workflow, it looks like a triangular box with a true and false execution. So it'll look something like that in workflow. So if you do get a question about workflow, it is the diamond shape. Okay. So this is just if these will execute or not. So our first thing is 3 greater than 1. Yeah, that's true. If statements only execute if it's true. If you want them to execute if they're false, you can use like a not symbol. So you can use if A is not greater than B. You can do it like that. And in that case, it will execute a false because it will change the false into a true. But it only executes the if it's true. So our second thing, this will is 3 less than 1. No, that will not execute. Now here's something a little more tricky, is if, and then a number. What is this number? What is this doing here? This is just to kind of show you that if statements follow what is known as Boolean logic. So if you have a number 1 exists, it has a value, that value is valid, so this is true. So this will always execute, always. because 1 is always true. Similarly, if you have a -1, that's still a value, right? So it exists. So that will also execute. If you have like 200, -1, etc., all those will evaluate to true. So if you have like a function or something that returns a 0 or 1, you just have to write that function in your if statement and just leave it there, because it will return a 0 or 1. If it has a 1, it'll execute. And if it has a 0, it won't. And in fact, when you do these comparisons here, like A is greater than B, that actually returns 1 if it's true. And if it's false, it actually returns 0. So if you check those in like a print statement, if you have like an if in a print statement, it will print 0 or 1, because those are what it's returning. Now we have a little mistake. So 0. Now 0, on the other hand, does 0 have a value? No. Yeah, 0 doesn't exist. 0 is like 0 or null. Null will also do this. It means nothing is here. Nothing to see here, nothing is happening. So this will come back as false. This will not execute. It will be false. Now on our option number 5 here, we seem to have probably made a mistake. So this is common when you're first starting out, is you're like, okay, if A is equal to 1. Nailed it, right? No. So what this is doing is it's still assignment, right? So it's saying, okay, I'm going to put the number 1 into my variable A. And it's going to see that if statement, and it's going to be like, okay, I can put 1 into A. I can do that. That's valid. And then it will execute, always. So it's basically returning a 1 no matter what. And so if you have that equal sign by itself, sometimes you don't want it to execute, but it will, because it only sees 1 equal sign. So in order to fix this, just do A equals 1. And that will actually check. So just make sure that your equal sign has 2 if you actually want to compare. 1 is for assignment, 2 is for comparing. Because basically the single equal sign kind of got stolen by assignment. So they still wanted something that looks similar, so they just put another one. That's what happened. These are just kind of list of like comparisons that you can make in an if statement. This is greater than or equal to, less than or equal to, if equal to, not equal to, and then less than or greater than. So those are just the different type of comparisons you can make in an if statement. You can also use them in a while statement, for statement, etc. Anytime you're comparing, you can use these operators. Similarly, if you have, like, say, f not a, and a is like 1, this will come back as false. It will take the 1, flip it to a 0, right? And so this will not execute. Or if you have a 0 and you put a not on it, that will make it true. So the not operator is a unary operator that basically, that basically gives you the complement of the thing. So a little more on Boolean logic. So as we discussed kind of before, numbers are a little bit tricky, but they just execute if it's a value. If it's no value, 0 or null, it won't. And then we're going to get to and or. So this is a logical and this is logical or. So the way these kind of work, if you have an if statement, so say A has to be greater than B, and it also has to not be equal to 1. Right? So this will only execute if this is true and this is true. If either one of those is false, it's not going to execute. If you change this to an or, then only one of them has to be true. So you could have a true-false, you could have a false-true, or you could have a true-true. It will execute. But your AND statement, if you have a false, false, it won't execute. False, true, true, false, it won't execute. Only true, true. Yes, question?
I remember, like, if you have a conditional like that, like, you have a bunch of ors, and let's just say, like, one of them is true, right? And it'll run, but, like, in the condition, it runs each argument, and it only stops at the one that's true if it's, like, an or.
Yeah, we will actually get down to that here. That's called short-circuiting, is what you're talking about.
Yeah.
So whenever you have multiple condition statements, also remember to use parentheses. Your compiler is going to start yelling at you basically after you have more than one.
Yeah.
It's going to be like, which one do I execute first? Because logical AND and logical OR are on the same level of precedence. So C doesn't know which one goes first. It needs parentheses. So parentheses have higher precedence. So it'll see those first. And be like, oh, I do the AND statement first, or I do the OR statement first. So anytime you have like basically more than one conditional, you want to use parentheses just to specify which one matters more.
Well, it's like, how would you know how much arguments it basically read before it stopped? You know, like, how would you?
Oh, yeah. So for short-circuiting, basically the way it works is if you have a logical, let me pull up a paper. If you have a logical AND, right, you know you need two truths in order to execute. So if you see a false right away, is there any point?
Yeah, of course.
Yeah, it stops. So it's like, okay, there's already a false here. My work is done. Toodles. Similarly, if you have a logical OR and you see a true, it'll also be like, oh, my job is done. There's a true here. This is always going to execute. So it doesn't even look at the second argument or the argument afterwards because it already found something that determined, okay, this is how it's going to be. So if you see a false in a logical AND, it's only going to take that one argument and then it's done. Similarly, if you see a logical OR, it finds a true, it knows it's done.
So basically, if you have a conditional statement, and in that conditional statement you have parentheses, right? You had like 5 or 3 or whatever, and it would choose like 5 instead of 3, and it would just stop. It wouldn't even look at 3.
Yeah, exactly. Because it already found a true.
Yeah, but then like within that conditional statement, if you have like another parentheses, it'll just skip this parentheses and move on to the next parentheses check for that argument.
It will do the parentheses first. So the parentheses have a higher precedence. So look at the parentheses first.
Okay.
It really depends how you've managed your conditionals. So if you have a parentheses that's the very beginning and there's an OR after it, it's going to look at that first and be like, oh, that's true, so I'm done.
Okay, but if it's and, it'll check the other parentheses and stuff like that.
Yeah, if it finds a false and it's and, then it's like, okay, I've got more work to do. Okay. So it does not matter. And this is known as short-circuiting. All right, so nested if, else if, else. So I'm just going to go over this a little bit. So when you have an if statement, it executes only if it's true. If you want it to execute something that's not true, you need an else. Now, if you have an if statement and you feel like you have more decisions to make, you need an else if. So it's like, if this is true, do some sort of code. But I also want you to track if another thing is true. So else if. And that's how you do nesting. And a lot of times you can write out a little thing, like here, true, false. And if there's another decision to make after the false, you know you need an else if. And if you have another decision after true, you know you need an if instead of an if statement. So in this case, if you have a decision here and a decision inside here, you need a nested if up here. So if this is true, we also do this. So this H problem, I will pull up. So the problem was, write a nested if, else that determines the age of a user, tells them they can drink, vote, both, or neither. So as we can see here, if the age is over or equal to 18, it does some sort of code. Then you have to check the 21 inside there, because that's another decision that you need to make. If that turns out to be true, you have a condition that executes only if the 21 came back false. See how that's like nested inside. And then else, and that's if neither were true. And you also put inside this print statement, you can't legally drink. So that's how to write like nesting. So we have to decide if they're over 18, then we have to decide if they're over 21, and make those decisions. Okay. Loops. Oh, no. What a piece of paper. Okay, so if we need to make a decision over and over again, we use a loop, right? So if you're taking in the number of like grades someone has, and you want to compare those grades every time, okay, you got an 85, so you get a B. You got a 90, so I get an A. And you're doing that every time, you need a loop. There are 3 different types of loops. So the while loop uses the key word while. You really only have one parameter in there. So you do something while, and then you have one comparison. So in this case, we have while I is not equal to -1. We're going to print out what I is. So this will go 3, 2, 1, 0, and then it's going to stop. Because it will stop as soon as I is equal to -1. As soon as it finds that to be true, but it's not equal to that. Or it finds that to be false, sorry. It will not do that. So 1 is not equal to -1, so that's true, so it keeps executing. But when it's -1 is not equal to -1, that's not a true statement, so it will stop. So while loops have a conditional, they will execute as long as it's true. Now, we have a common mistake here. That semicolon is very naughty. So after this semicolon, it's going to see that as what it's executing. It will actually read this part as a separate thing. It won't read it as part of the loop anymore. So what this will do is it executes nothing forever. It's an infinite loop. So you have to be really careful when you're writing code not to make that mistake. They might also try to trip you up on a question and have a semicolon right there. The answer is it loops infinitely, and it never actually gets to this part down here. For loop has 3 parts. It always has 3 parts. So in this case, we're just going to 0 to 4, and it just goes up every time. So the way the for loop looks is you have a pre, you have a condition, and you have a post. So the pre is what it does first. So in this case, we're just setting I to 0. We're just setting up our loop. The middle one is your condition, what you're comparing. If you have some logical ands, logical ors, all that stuff's going to go in here. And then post is what it does at the end. So in a while loop, you need to update I somewhere. In this case, we did it inside the print statement. But you need to update I, otherwise if you're using a counter-controlled loop, it's never going to stop. You need to change something about the loop in order for it to stop. In the for loop, it'll do that I++ like right here. Instead of it heading at the bottom like a while loop, it's inside, right? It's right here. So if you want to convert a while loop to a for loop, you have to take the I++, put it here, or similarly put the I++ at the bottom of a while loop. The pre in a while loop will just go outside the while loop, so you initialize I at the beginning. And then the thing that keeps them the same is they both have a condition inside of them. Now this over here, it looks a little funky, but this is perfectly valid. All a for loop needs is those 2 semicolons. That's it. So if you don't have a pre or you don't have a post, that's okay. As long as it's got the right amount of semicolons, it will execute. So in this case, this is going to loop forever. It's not comparing anything. It's not updating anything. It just loops forever. But it's valid. So your compiler will actually not yell at you for this. It'll be like, that's okay. Our do while loop is a while loop with like kind of an extra. So the do in the do while loop always executes that thing at least once. So this will print yas, and then it will stop. Because while 0, well, 0 is false due to Boolean logic, and then it stops, right? If I had a while 1, it would continue yas over and over and over again. But this will just print the first thing at least once. So that's the main difference between do whiles and for and whiles, is that your do while is always guaranteed to execute once. And then afterwards it checks the condition to see if that's true or not. So sometimes you want to take in a scanf or something at the beginning. You don't necessarily want it to do every time, but you want it to do at least once. You want it to take in a number at least once. You'll use a do while, because then you're guaranteed to have that taken in once. So it does. And it's different from a while loop in that a while loop needs to be true in order to execute. This doesn't need to be true to execute at least once. Okay? So that's just the main difference. In our loops, we have something known as break and continue. So sometimes you want to leave the loop early. Sometimes your value turned out to be something you didn't want it to be. It went negative when it wasn't supposed to be. So you can have a break statement. You can have like an if this somehow turned negative, I want you to break out of this loop. So I do have a problem where we wrote a loop to add a total as long as the numbers aren't even. So this is while 1, meaning it's always going to execute. It's always true. Right? While 1, 1 is true. It's going to ask the user to enter a number, odd to stop. It's going to scanf. Scanf function, you need the specifier, so we're taking in an input. Make sure to use the ampersand, because the ampersand is telling it where it's going to go. Then we have our %d, so that whatever the input is, it will put it in as a integer. So if I put 3.0, it will put in 3. It would truncate it anyway, but that just kind of helps scanf do its job. Then it compares if the input is odd. So if it's odd, we break. Else, we're going to add that thing together. So if we run this, we do a 2, we do a 4, and so we do a 3. So as soon as we put in the 3, it broke out of the loop. It's done. Then it added the 2 and the 4, and it ignored the 3 there because it saw the break first. So then it added it all up. All right. And all you need for a break is just the keyword break. That's it. Oh, nope. Continue is kind of the nemesis, or like partner to break, is continue. So what continue does is it basically like skips a thing. When a while loop or for loop encounters continue, it starts over. It's like, okay, I restart. You go back up to the beginning thing. So if we have like a while, and then we have a continue, it will stop whatever it's doing. It will not execute the rest of the loop. It goes back up and compares right away. So this is like if you have a case where you want to skip something. So say you have a loop that you want it to exit out of the loop if it's a negative number, but you want it to skip all the odd numbers. You would use a continue. So I'll pull that up. So in this case, we are going to compare the input to make sure the input isn't negative. It tells the user that a negative will stop, and then it'll give us a little message saying, no odds, please. So put a 1. No odds. As you can see, it's not going to add it to the total either. It's going to continue. It goes right back up and compares again. So we have a 2, we have a 4, and we have a negative 1. As you can see, it adds the 1 and the 4. Sees a negative number, and we also need to put an else if there. We can't just put an else because we do need to compare what the input is. Because it could see that it's odd, and then it's just like else, and then it puts everything into it. And we don't want to put everything into it. We don't want those negative numbers. We don't want to add negative numbers to our total. So we do need an else if there because we don't want to add that negative 1 into our total. We wanted to exclude it. So we have this case here. We will have while I is less than 7, if I is 2, we continue. So the problem here with this is we go 0 is less than 7. Okay. 0 is not equal to 2. We add 1. And we keep adding 1 until we get to 2. And then we see 2 equals 2. Continue. 2 is less than 7. 2 is equal to 2. Continue. 2 is less than 7. So unfortunately, we've created an infinite loop in this way. So when you're using continue, you do have to be really careful that code isn't creating infinite loops, because it can. If you just have a continue by itself with a comparison, it could be comparing that thing over and over and over again, and it never stops. So the way to fix this is just to add our I++ in here. We add we add a block, and we add I++ in there. That way I is updating, and then we continue, and then we're like, okay, now it's 3, and then we loop until it's 7, and then it won't execute at 7. Switch statements. So switch statements are another way of writing if, else, if, or if, else, if, else. They're another way to do that. It's another way to express it. We will skip this, but I will post it later. So in the following code, we have a character A. We compare this A. So what switch needs a case inside here. So this is your case. This is what you're checking, right? And so our first case is if that character is A, it's going to print a certain thing. Now, there's a little problem here in that there's no break statement. So what this is going to do is it's actually going to print A and B. Now, if you don't want that to happen, you're going to have to add break statements. Switch has a problem known as falling through. So if there's no break statement to tell it to stop, it won't. It'll just go to the next case. Be like, okay, I'll print this case, print that case, print this case. Right? It just follows all the way through. So you need a break statement telling it, okay, you need to stop here. And then at the very end, we have something called default. It's just by itself, and then it has some code to it. This is the same thing as like an else statement. So just the very bottom, it's default. That's if all your cases have failed. And it found nothing, so you have default. A lot of times default is for where there's an error. Somehow the user put in something that we didn't want anything to do with it. Like you're comparing characters and they put in a -1. And you don't have a case for -1. You didn't want -1. And so like the default is like, please input a valued thing, please. So it's kind of like your if, your else at the bottom. Any questions on loops or break. Loops, break, switch. All good? Sweet. Oh, hooray, we made it to pointers. So what type of data does a pointer contain? Pointer's my favorite. So what type of data does a pointer contain? A pointer contains an address. Pointers are initialized. You need to decide a data type. What type of data is it pointing to? It can be the same as your regular data types. You can have a pointer to a float, pointer to a pointer to an int, pointer to a double, whatever it needs to point to. So in this case, like say you have an int, you want it to point to like an int a, then you need like an int star p. It has to correspond to something that it's pointing to. So if you have an int a, you can't use a float pointer. That won't work. If you have a float a, you can't use an int pointer. It won't work. It's specifically an address to a specific type of data. Right. So we have this code here. So danger, something very bad has happened. So in this case, I will draw it out. If I can find the things. Draw it out. So what's happening in memory is we've created A. We've created P. Right? Now, A just has garbage in it right now. Just some garbage values in A. Similarly, there's some garbage address in P. So this is also garbage. It's a garbage address inside it. So that garbage address can point anywhere. It can point outside memory. It can point outside your program. It can point to something important. It has no restrictions. So it goes where it wants and it does what it wants. And 99.9% of the time, you don't want that. It's going to access something you don't want it to. So in this case, we are dereferencing a pointer that hasn't been initialized. So this is taking some garbage values that's going off into the void. It's wandered off into the void. It's wandered off into space. And then it's just like, oh, put a 5 in there. Put 5 into nowhere, or into space, or not into nowhere, but into a random place in space. Maybe outside the program. Maybe where main was initialized. You know, it could be wherever. And so it's putting a 5 into a really dangerous place. So we don't want it to do that. So the way that you can fix that is to make sure the pointer points somewhere valid. So in this case, we want it to point to the address. So A has like an address, like 0xAA, something like that. And we want it to point to valid address. So we tell P, point to the address of A. Oh, that's an ampersand, sorry. So use ampersand for addresses. So this goes up and grabs this guy here and puts him in here. And now P has a cool place to point to. So when you tell it to put 5 somewhere, when you dereference it, tell it 5 goes into where you're pointing to, well, it points to A now. And A can definitely take in a 5. It's an integer. It's cool. So it wanders down to the address of A and puts 5 here. Now we're A-OK. Now we're good. Similarly, you can also have problems. So pointer language for 0 is null. It's basically 0x000. It's basically saying no address whatsoever. So it also has a very similar problem in that P basically points to nowhere. Move that up. P points to nowhere, and we're telling go to the address of nowhere and put a 5. Yes?
So the int pointer to the address of A, would that like to fix that like fixing it could like you put underneath the pointer to equals 5? Is that what you're saying?
You could fix it by interjecting here pointer P equals the address of A. Yeah. Or just write it in your int star P equals the address of A. Yes, it has to come before. So like P has to know where to go that's valid. So right now, if you tell it to go somewhere random in memory, some garbage address, then it's going to go to that garbage address, and you don't want it to. So also, if it's null, just is pointer language for 0, so go to nowhere. and put 5 in absolutely nowhere. Well, you can't put 5 in nothing. It's basically put 5 in where space doesn't exist. 5 needs some space for it to exist. So this similarly this is called dereferencing a null pointer. And we also don't want to do that. Right. So what we would have to do to fix this is make p point to some sort of integer. Because we can set it to null, and that can kind of avoid garbage addresses. If we want to avoid garbage addresses, that's nice. We can set it to null. That's great, because instead of pointing like somewhere in space where we don't want it to, it just points nowhere. We just have to update it later. We have to tell it a valid address later. This results in something called segmentation fault, which means you ran out of memory, or you went outside of memory. So big way to seg fault is dereferencing an uninitialized pointer or dereferencing a null pointer. You could also do it by looping way too far out of like an array or something. It's basically your memory has this space here, and when you go outside here, where your program doesn't have any memory, that's a segmentation fault. You just went outside where you're allowed to, out of bounds. Okay, functions with pointers. So we saw that swap prototype earlier, but we didn't write it. So we're going to recall our void swap. So we're going to write it. So the way I like to do pointers a lot of times is to look at, like, say you're doing a main. How would you normally like swap something in main? So you can't really just set A to B, right? Because if you have an A, like say A is 2 and B is 3, if you assign B to A, 3 goes into A and then you lose the 2, right? So you're going to need like a temp and say A goes into that temp. Okay, so now you have a new variable. Let's get temp. Okay, and now it has the value of 2, right? And so then now you can set them to one another. So now it's 3, 3. So this gets updated to a 3. And now you can set B equal to temp. So inside main, that's how you normally do it. But say we want to allocate to that to a function. We want a function to do that for us. Now functions are kind of restricted in that they can only return one thing. So in this case, we want to change 2 things. So we're kind of forced to use a pointer instead. So we'll do similarly what we did in main, but using pointers. So we have void function. And the reason we want it to be void is that we're not really returning anything. We could return something. We could return whether or not it executed properly, like a flag or something. But in this case, we're just swapping 2 numbers inside of main, so there's no need to return anything. Okay. So we have an int star x and we have an int star y. So these need to contain inside our swap function. We just have x, and we just have y. And they need to contain an address. So in our main function, what we need to send them is an address. So in main, say we have an a and it's 3. And we have a b and it's 5. This is inside our main function. And so when we call swap, we need to send it the address of a and the address of b. So now inside our x, we have the address of a, and inside our y, we have the address of b, which is exactly what we want. Okay. So now we can use those to swap them. So we do the same thing that we did before. We do our int, temp. But instead, we need to dereference. We need to get to where x is pointing. X is pointing to a, so we need to dereference x. So we do star x. And now we can set them equal to each other, so we need to dereference both. So inside main, we have our a, which is 3, and our b, which is 5. And right now, they're both 5, right? Because we've gone to their addresses and said assign them to the same thing. And inside our swap, we also have temp. So temps are kind of like our little treasure chest. So it has the 3 still. But main doesn't know that. Not yet. Right, so it's 5 and 5. Right. So then we have to set y to our temp. And then inside our main function, now this is 3. Okay. So we kind of got around the scope of main by using the pointers. But because we know where A and B are in memory, we can kind of circumvent the fact that main doesn't know anything about swap. Main may not know the variables that are inside swap, but swap has the addresses of the variables inside B. So it can manipulate them however it wants, because it knows where they are. So wrote that. We'll skip this. It's very similar in that you just compare the dereference to x and y. So star if star x is greater than star y, return star x, else return star y. So it's just showing anything that you can do pass by value, you can also do pass by reference. It's just the variables will be different. So you can easily achieve the process, in this case, with either one. You just have an int return value because you were just returning one value that's max. So you change it from void to int. So that's why. Is returning a max. Any questions on pointers so far? Clear as mud? All right. So then you have pointers. So a pointer can also point to a pointer to like a variable, right? So in this case, we'll just look at this following code. So we have an integer a. In this case, we're going to want it to point to the address of a, right? And then now we have a pointer to a pointer, and we have a pointer, right? We have an integer pointer. So we're going to create a pointer that points to that pointer. So this will go to the address of p. So what's happening in memory is we have our a. It has an address. We have our p. It has an address. We have our q. And it has an address. And so this is kind of like a little level, right? A's here, P's here, and Q's up here. Right? To move up, you kind of use that ampersand. And then to dereference down, you use however many stars it's gone up. So in this case, we're going to place our address of A here. Now P knows where A is. And now Q knows where P is. And so because Q knows where P is and P knows where A is, we can use Q to actually manipulate A if we want to. We can also use Q to manipulate P as well. But this wouldn't work if P didn't have A's address, because then in that case, Q knows where P is, but P doesn't know where he's going, right? So it has to like chain up. Everybody needs to know where everybody is, right? So as you add on more pointers, they all need to have address. Basically, you have to be able to go down the go down like a little maze or whatever. It's kind of like, where does this go? Okay, it goes here. Where does this go? It goes here. Right? So if we want to use Q to change A, we just did that. Because it's 2 levels up, so we use 2 stars. So it dereferences itself, and then it dereferences what it's referencing to. So it's saying, go where you're pointing to. So it points to P, so it goes there. Then it sees another star, and it's just like, okay, go where that points to, which is A. So you can use Q in this way to manipulate A. So this code has a lot of problems, right? P is not pointing to anything in particular. Q is not pointing to anything in particular. And then we dereference Q. So this is even worse. We go to a random address that points to another random address, who knows where. So this is actually even more spooky scary than what we saw before, right? Because we're dereferencing an uninitialized pointer not once, but twice. So in order to fix this, we just need the addresses. Here. Okay. And this is the address of P. And now we're safe. We're good. All right. Any questions on pointers to pointers? I know it's a little convoluted. Oh, okay, all right. Sweet. Yes, of course. What? Yeah, sure. So the reason that this is like a problem is because neither of them have an address, right? So they both need an address to know where to go. And so a pointer to a pointer has to point to this type of data, right? Because it's 2 stars, it needs to point to a single star. And all the data types have to match. So if I have a float star star Q, it's not going to work. Yes, yeah. So yeah, Q wouldn't know where to go. So if I had just this, oh, can't even see that. But if it was just star P and then you set an address for Q, and you do star star Q, that's a big problem because P doesn't know where to go. Because it's telling it, okay, I'm going to go to the address of P, and then there's another star, so it's like, go to the address where P points. Well, P doesn't point anywhere good, right? And so we're still putting 5 up in the Netherlands, and we don't really want to do that. So you have to fix both in order for it to be valid. And all the data types have to match up. So if you see floats, they all have to be floats. Okay. So file I/O. So now that we have pointers, we can use them for our file I/O. File I/O is reading from like a text file. So in order to open a text file, we need the function fopen. And let me call it like that. So fopen just opens up the file. Oh, where did I put it? Just give me 1 second. I just have to find my papers. Wherever they went to. Because I just have all the syntax and stuff written out for you for, here they are. Sweet. All right. So when you're creating like a file I/O, you need a pointer and the file data type. So you'll need to write like file star fp equals fopen. And then you need the name of that text file. So you can hard code it as a string, or you can get it as like an argument from your main. I'm not sure if you guys have seen main int arg vc char star star arg vc. If you have seen this, this is taking in stuff from the sorry, give me a moment. It's taking stuff from the terminal or your command function. So like when you GCC something, you can put in like a name. And so the first one is taking the number of arguments that they have, and this one is taking in like a file name or something. So you can do it that way, where then it's taking in your argv2 or something. And you can have that there, and that will take in the string. Or you can just hard code the name. It depends on what you're doing with your file I/O. And if the name changes all the time, then you're going to want to use something with a command line. If not, you can just put the name, like output.txt. That's fine. So this is just the various functions that you can use when opening a file. So fopen just opens. And its syntax is it needs a file name. So just fopen file name. And it can get that file name from various places. fscanf is going to read an input. So it reads. So this is you've already created like an output file and you want to import it into your function. We'll look at a function that has like a list of names in an output, and then it just prints those lists of names to the screen. So it needs the file. So in this case, it's going to be like our FP. It's going to need whatever pointer you created, so like your file pointer. Like what type of thing you're going to read. A lot of times it's like a string. Sometimes it's a character, sometimes it's a decimal. It's whatever conversion specifier you need. And then its destination. So if you're reading in a string, you have to create a string that it goes into. A lot of times you use something called like buffer, and then it's like got a really long thing. Like say it's, so you have like buffer 1024. And so I'll read that buffer and put it into your destination. Did I go over strings now? No, that's later. Okay. Okay. So this is basically grabbing your FP up here, and then what you're taking in and where it's going. Right here. Okay. fgets is also like a reading function. It's your string, or whatever you're taking in, how long it's going to be. So say it's like 60 or something, 60 characters long, and then your file again. fscanf will, like if you encounter a space or a new character, it'll stop. fgets will just take in whatever. fprintf is instead of a read, so these both were read functions. So they read from a text file. Your fprintf prints, it's a write function, so it writes. Oh, I'm very sorry. You need to tell fopen what you're doing. Yes. It's your mode. I'm very sorry, I forgot about mode. So R is like for writing, or reading, sorry, reading. So you just put in like a string, and it tells you like, fopen, we're going to read from a file. Write, append, and R plus is read and write. And then W plus is read and write from a new file. Sorry about that. Yeah. So you need the file name and then the mode, like what you're going to do with it. So if you're going to read or write, like what are you doing with when you open it? Okay, so this also writes. So it needs like your FP. And it needs like what format. So a lot of times like you just put the string hello. It's just whatever's going into that file. So it's like, in this case, you'll have a W here to write. And then when you call your fprintf, you'll call the FP. And then you say, OK, I'm going to put the word hello there. And that's what that is. fputs is then like your string. And then the file name. It just kind of switched. And then whenever you have an fopen, you need an fclose. And fclose is just whatever the file name was, just fp. So whatever you named this up here, you're just going to close it. When you open something, you close it. It's just because otherwise what happens is you have lost memory. So you've opened up the file, but that memory stayed like floating around somewhere. And so you want to close it so that memory is like, okay, we're done. We're done with this. So I'm just going to pull up the function for if I can find it. No. Oh, this computer does not like me. Oh, no. All right, so in this case, we have our buffer, because we're going to be pulling from a text file and outputting it to the screen. So we have our text file here. It's just going to output 01.txt. I hard-coded it. We're going to be writing. So that's the mode that we're going to be using is writing. Whenever you have like a fopen or you create a pointer, you can always check if that actually did what you want it to. So in this case, we opened to this pointer. So we have to check if that actually happened. If it didn't happen, it will be null. If it did, then we're ready to go, and it did what we wanted it to. This is saying we're going to keep scanning in stuff. We're going to keep scanning in strings as long as we haven't reached the end of our file. So in programming, when it reaches the end of like a text file, it gives it like a certain value. I don't know what that value is, but it'll give it a value. It'll return a value, and you can check that value just with it's known as EOF, or end of file. And in this case, we're just printing what is put into buffer. So in this case, we have just a list of names. We run our function, and hooray, it prints the list of name that was in our text file, and that's what we wanted it to do. And then we reach the end of file, and then we stop. We close up our stuff. I just had to add a little thing. I just set our pointer back to null, just as like a little added cleanup. But that's not always necessary, but this F closes. Yep. All right. Any questions about file I/O? All good? Sweet. All right, so Ascii. So every single character also has a numerical value. This is a set thing. You can look up an Ascii chart. It will tell you like lowercase a is the same as 97, and higher case a is like 43 or something like that. The way you can kind of check these is you can actually write conversion specifiers. So if you have the character a and you want to check what its numerical value is, you can put %d and then comma, whatever that character is, and that will tell you. So in this case, as we see here, it's a character a, where we're telling it to convert that character into its numerical value. That numerical value is its Ascii value, and that will be 97. Similarly, if I have an integer that's 97, in this case, I have an integer that's 97, but I wanted to convert that 97 into its character Ascii value, you can do that with %c. The reason this works is it's just a conversion specifier. So it's just telling you this is an integer, but we'll just take whatever value that is and we'll print it as a character, as if it were a character. It doesn't change it, like in memory. It still stays 97, but now we can see 97 is a lowercase a. We will probably write, I'll pull up this Ascii thing that I wrote. So Ascii also has a difference between the character one and an integer one. They're different. They're different things. They actually have different values. So just a very simple showing how ASCII works. So this is just a function that just prints ASCII values and what their numerical values are. As you can see, just all these have numerical values. So as we can see here, 49 is what the character 1 is, which is not the same as the integer 1. So if you have a string that has numbers in it, you have to be very careful because they're not necessarily going to be the same value as the number 1. Right? So if you have a string that's like, hello, 1, 2, 3, and you want to grab that 1 and do something with it, you're going to have to subtract it from the character 1 and add 1 to make it like a 1, because otherwise it's 49. So that's our function that just prints ASCII values, just demonstrating that character values have a numerical value, etc. So this one was 49. This is 65. This is 97. So those are their values. So now arrays. An array looks like this in memory. So an array is a consecutive piece of data. So it has like a name. So say the name is like array. And each piece comes right after another, and they're all associated with each other. So basically you have many integers or many characters associated with each other and kind of put together as one. So is the data in an array consecutive? Yes, it is consecutive. So one comes exactly after one another. There's no space in between. So if you have an index 0, right after is an index 1. You initialize array just by, you have to tell it what type of data the cells are going to be. So you have, like, say, an int array. This will tell it how big it's going to be. So in this case, we have 1, 2, 3, 4, 5, 6. And we can either end it there. If we end it there, all our cells contain garbage data. We haven't initialized to a thing yet. We can initialize it to a thing by doing like 1, 2, 3. And in this case, C is going to be actually really nice to us. Because once we've told it we're going to assign some values, it will actually set the rest of these values to 0. It'll do 1, 2, 3, and then 0, 0, 0. It will not leave them as garbage, because it's like, okay, we know we're going to do something with this array. We only know part of it, but we'll be nice and put some zeros at the end. But if you don't have this here, it is, it's going to give you garbage. The index of array always starts at 0. And it's always going to be 0 through 1 less than whatever your max was. So in this case, we have 6, so it'll go 0 to 5. Those are its indexes. So we have the following code. We have the 1, 2, 3. It's going to 0 to 5, so it starts at 0. So this is going to access. So we have our array. We have 1, 2, 3. Or actually, it's 5. Right. So we have our 1, 2, 3, 0, 0. So when I is 0, it accesses 1. Right? So it'll give us a 1. When it increases I, so then our index is at 1. So the index 0, index 1. So then we'll print a 2, 3, and then 0, 0. Now, if we have a loop that goes past our index for our arrays, it will read that up to a point. It will probably give you garbage. It'll read that up to a point until you reach the wall of your program. So for arrays, you can go like a little past it, like 10 or 20, you can go past. You'll get garbage. You'll get things that aren't allocated, but you can go past a little bit. As soon as you hit this wall, though, you will segmentation fault. You're donezo. So if you have a loop that's like a billion, it will loop through those couple of things, and then all of a sudden it'll go outside of memory, and then it will segmentation fault. So there's a little leeway in between here, the end and the array. And then what values is just 1, 2, 3, 0, 0. Now, a lot of times when you write an array in main, you want to send it to a function. So the way arrays work is they are, so what you send in the function call, so say you have a max function. You have a max. And this is inside main. And it's void. So you have a max function. So all you really have to do is, so you have like an in array of like 5. And it has like 1, 1, 1, 1, 1. Max will just return 1, but that doesn't matter too much for our purposes. So you just have to send it the name of your array. That's it. You'll also probably want to send it the length, how big your array is, so it knows how far to loop. Say if it's like looking through, it needs to know how long the array is, so you'll probably use an n. And that's it. Now when we're writing this max function, we want it to return an integer value of what that maximum is. But what it takes in is actually a pointer. Because what you're actually sending over is the address of the first element. You're sending over where the array starts. So each element in the array has an address. And when you send over this name, you're sending over the address at the beginning. And that's super helpful because arrays are consecutive in memory. So as soon as you have the beginning, you can access everything else, right? So actually in our max function, we can just use array normally. We can set max to the first element, and then just compare if max is less, and like we would write like a for loop. I++. Okay. And then we compare if max is less than the value it finds, in which we'll return. We'll set max to a new thing. Yes, question.
So in the actual like function, don't you use the pointer array, just the array array?
Yeah. So we have named it array in this case. So whatever your pointer name is, that's the name that you'll use. You're just using a different name, but it's past the address.
Okay.
So you can name an array. You can name an array 2. You can name it anything you want, because it has the address of the original up here. So it's actually accessing the array that's in main. So when it's going through, it's looking at this array that's still in main. And the only variable that's the scope of this is max. This is why we need to return it in our int. Because it's the only thing that main won't be aware of is like max int of our array. And we set it to the first element because we know that's a valid thing. So we don't want to set it to 0 in case maybe our maximum is -2. We don't want it to return 0. We want it to return whatever that maximum is. So you do want to set it to like an element. And a good element to set it to is the first one. And then you can just compare it through a for loop each time. If max is less, then the new max needs to be whatever the array was, that array element. And at the very end, you will return max. Or int, a max int, in this case. So the parameter that will hold what we're sending is a pointer. And it has to match the type of cells, right? Because we're sending the address of an integer, the first element of an integer array. So the pointer has to be an integer pointer. If we're sending a character for like a string, we'll have to change it to a character pointer. That's just to make sure it matches. So matches and a pointer. And then we did this max function. Here. So the max prototype will look like max, int max, int star array, int n. That's what the prototype will look like. The reason we need a pointer is, again, we're just sending an address, and arrays are technically a type of pointer. Pointers aren't necessarily arrays, but arrays are pointers. Because it points to where its consecutive data starts. It's like, okay, it starts here. And then you hop over however many you need by the index. And it knows how many to hop over because it knows it's an integer or a character. So it knows each cell is exactly X amount of bytes, X amount of bits. So we wrote the max function. Good. Return max. Min is super similar. You just change the sign. So instead of looking for something that's less than max and changing max, you would look for something that's greater than max and then, or greater than min, and change it. So strings are a type of array. So as an example, you have like hello. Like that. So they're super similar. They're consecutive data. They just contain characters. The difference is at the very end you need an all terminator. It tells it where the string has ended. So basically it's an array. It's a character array plus 1. We don't have a super ton of time. We have like 10 minutes left. I'm sorry, I've got a little short on time there. Let me see. So strings are the same as arrays, just character plus 1. Our string functions, so our string length tells us how long the string is. You just tell it the string name. String compare compares two strings, so you have string 1 and string 2. It will return 0 if they're the same. So if you want to in an if function, you need an exclamation point for not. String copy is used a lot if you have your file I/O. So it will copy your first one is your destination, and your second one is your source. String cat is string concatenate. It adds an element to the end of the string. You have to be very careful with this because your string might be a set amount length. And so you don't want to add to something and then run out of space. So be careful with string cat. And string string is haystack needle. So string string says, okay, we have a large string, that's our haystack, and then the second one is the needle, like what we're looking for. So if we have what's up, and we're looking for the word sup, it will return the word sup. Okay. 2D arrays are a coordinate system, like this. The first one is your rows, and the second one is your columns. So these are your rows, these are your columns, like that. And you can loop through them using 2 for loops. So one will be the rows, the first for loop will be the rows, and your second for loop will be the columns. Okay. So you have an I in your for loop. Your I is your rows, and then inside you have like a J. Your J is your columns. The J will loop through faster, and then your rows will increment slowly. So it's kind of like you have a 1, there's like 1, 2, 3. Then you have a 2 that does like 1, 2, 3. And that's how you loop them through them. So like a coordinate system. Do passing arrays. Dynamic memory allocation is when you don't know how long your array is or how long your string is. So you have to use something called malloc. It's located in your studio lib. And in order to do this, you need a pointer. So say you need like a char pointer. Use malloc, and then you need the size of, like your char. And then you need to times it by like a length. And in this case, if it's a string, you need to add 1. If it's an array, if you have like an int star p, p equals malloc size of int times n. And this basically creates that array for you. So you can ask your user, how long is this array going to be? And that way you know that it's 50, you can create a space of 50 things. Malloc means memory allocation, and calloc means clear allocation. So memory allocation, you do it like that, right? You create the number of cells. But there's garbage in there at the beginning. Calloc will set all those cells that you've put in to 0 or null. And so it has a different syntax, so you call calloc. It also needs a pointer. So you have calloc, and then you have how long, or how many elements. And then your size. Okay. Structures are user-defined data types. So if I want a data type that contains many things inside of it, I use a structure. So in this case, we have a structure that has student info. It's got a pointer to a name. The reason we have a pointer to a name is so we can allocate the name later. So name equals malloc size of char times n plus 1. So you can ask the user, how long is your name? And you can malloc it later. Right now, this hasn't created any data. When you create your structure, it's just defining what the structure is going to be. So you haven't allocated memory yet in this case. You only allocate memory when you call it later. So in this case, if you want to call this later in main, you use struct student info new student. You need the entire thing because your data type is struct student info. Right. If you can type def, I just want to do type def real quick and then we'll finish up. Type def student info, and then you have your data, and then you can name it like Ascii. And when you call it later in your function, you could just say Ascii new student. That's all you need to do with type def. In this case, the little error here is that. Because it's a data type, it's like if you were to say int, right? It needs a semicolon at the end. So that's the, and then if you type def, just make sure you have the name that you want it to be called. And that. All right, questions, comments, concerns? We are out of time here. So any questions? Yes. Does what? Yeah, so every malloc call that you have, you need a free call. So when yeah, so if you have a calloc, you also need a free. So when you malloc or calloc something, you're creating space and memory. And so free says, okay, we're done with that now. Free up what we created. If you did not get a survey, I have more surveys. So if you could please fill those out. Huh? 47, yeah. Who needs a survey? Here you go. And then if you could just hand those to me when you're done. Thank you. Oh, sorry. Yes, I will post the solutions like an hour or two after this is all wrapped up.